I somehow managed to not get this question recorded in either class yesterday, so I thought I'd make a quick video walking through this just to make sure that you've got a place to look back at it if you want. So this is where we're building that fence. We've got an area that we want to enclose, and we've got the front part of the fencing we're going to use a little bit more expensive material, and then the other three sides we're going to use that less expensive material. So I do think it's a good idea to draw a quick picture. We've got, this area that we want to enclose. The length of the side there is X. You could call it length if you want. And then our width is going to be Y. And then I also like to put on here that we've got that front side here. That's going to be $70 per meter. And then our sides are $40 per meter. So is the back. And so is this other side here. So this is kind of helping me think about that cost function, that it's going to be $70 times however long the front is, which is X, plus $40 times however long the back is, which is also X, and then $40 times each of our sides, or $40 per meter times each of our sides, and that's going to give us our total cost. We can go ahead and combine like terms. This is the function that we're going to want to minimize. This is our objective function. So maybe we'll write that here, that this is our objective. But we also have our constraint that we need our area to be 92,950 square meters. So that is that objective or constraint, or however we want our constraint, not our objective, that's our constraint, or our restriction. So we can use that constraint, we can solve it for X or Y, it doesn't really matter, it's up to you. I tend to solve for Y, but you don't have to, it's all for X. But we're going to take and plug this into that objective function right there for Y, and we're going to get that our cost is 110x plus 80 times that 92,950 over X. We can rewrite this just a little bit so that it's a little easier for us to take the derivative. If we multiply that 80 times our 92,000, we're going to get 7,000 or 7,436,000 times our x to the -1. Now that we're here, we can take the derivative of that cost function and find our critical points. So we've done the real hard work. Now we're to what we're sort of used to be doing, where we take that derivative, set it equal to 0. And I'm just kind of cleaning things up a little bit, multiplying that -1 times our 7 million, putting our x squared back on the bottom of the fraction. And we have solved a bunch of problems like this before. Oh, there's no x on our derivative. It should just be 110. So let's write that out a little bit nicer. 110 there. But if we want to clear out this fraction, that x squared that we've got right there, if we multiply both sides by x squared, that is going to cancel that out. It is going to put an x squared multiplied by our 110, but that makes things much easier in terms of solving. We just need to solve for x squared. So we need to add that 7 million number to both sides and then divide both sides by that 110. We'll get 67,600 when we do that. And then we'll take the square root of that, and we'll get plus or minus 260. So we would not use the -260. That is not going to be a critical point that is in the domain of the situation that we're talking about. So it's that positive 260. We're pretty sure that that's probably going to be where our minimum is, but we should verify. That's always a good idea. So we can verify with the first derivative test or the second derivative test. It's up to you. But if I'm going to use the first derivative test, we need to look at a number that is before that critical point. And I try to pick the smallest number I possibly can. I can't pick 0 because our derivative is undefined at 0. That's actually another critical point that we have here, but it doesn't make any sense to have x being 0, so we're not going to use that. But that's why we've got to look at 1. If we plug 1 into our second derivative here, we're going to get that 110 minus that 7 million number. So that first derivative is going to be a very big negative number. and that tells us that we're decreasing. If we plug in 161, we are, and sorry, I drew my inequality incorrectly there. There we go. We are going to get something that's just slightly bigger than 0. It's almost 1. When you take and plug 261 into this part here of our derivative, you get 109 point something something something. So when you subtract your 110 from that 109, you will get a positive number, which tells us that we're increasing. So we do have a minimum there. You could also take the second derivative, plug in that critical point, and show that you're concave up. That would show that you also have a minimum. So that is going to be the length of the front and back of our fence. If we want the y value, that's where we can go back up here to our constraint. So x is equal to that. Y is going to be equal to that 92,950 divided by 260. And that's going to give us 375 or 57.5. Then if we want the total cost, what that actual minimum cost is, we can go back to our original cost function and plug in the dimensions that we found and grab our calculator. And sorry, I'm grabbing my calculator and I'm plugging in these two numbers, and we get that it's 57,200.